Hello everyone, welcome to MLAS 700, Learning Activity 15, and this is part 2 of our machine learning models focused on diving into unsupervised learning. We're going to take this lecture and we're going to use this time to compare and contrast between unsupervised and supervised for a couple minutes. And then from there, we'll move on to diving into principal component analysis, which is a very common unsupervised machine learning algorithm. One of my favorites. It's been around for a very long time, so we'll dive into the math on that, and then and we'll actually do as part of one of our labs this week. We'll do a Google Colab. We'll set up a Colab and run PCA. In that environment, and then and that'll be our first lab for this week, and then we'll circle back with Arduino for our third activity for this week's learning activities. Okay, so the big difference between unsupervised and supervised is labeled versus unlabeled. So supervised has labeled data, uses training data. Whereas unsupervised doesn't have labeled data. It's unlabeled, and it's just going off and finding raw patterns and recognitions without having any pre-trained or pre-labeled data to support where the model or where the math goes. So typically in an unsupervised situation, we'll call that clustering. So anytime we do any type of categorization of data, there's two big buckets. There's classification, and then there's clustering. Clustering is unsupervised. Classification is supervised. So when you hear that, like predictive classifier or predictive classification or just a classification process, when we say the word classification, that means that it's a supervised learning model. If we say clustering, then we're usually using an unsupervised learning model. There are different algorithms, there's different math and different process. So typically for unsupervised, this is also something that can be used on the supervised side as well. But there's computational complexity on the supervised that the unsupervised doesn't have. So typically, not always, but unsupervised algorithms typically run pretty quick, a lot faster than your supervised. So PCA is one that we're going to dive into today in more detail and go through the math. Is been around for a really long time, and it's computationally very quick, and so it's very efficient, and you don't need a GPU or anything like that to run PCA. So that's kind of the beauty of principal component analysis, what you can do with it is clustering, of course, using for customer segmentation. You can use it for outliers and outlier detection, exception handling, divergent data, any type of things that kind of you can see that's going to be outside of the norm. Typically is good for anomaly detection. So PCA is good for those kind of problem sets. There's a lot of algorithms out there. K-means is one. It's not just PCA. There's another one that's a newer one that's been out for almost 10 years now, called DB-Scan. That's a good one that I like to use as well. Another one is T-SNE or Stochastic Nearest Embedding, and that's another one out there. That's a newer one as well. That one's a little bit more computationally intensive, but is really pretty cool when you get it working on a tensor board. So that's there's some really neat things you can do in that arena. Okay, so unsupervised learning. One of the there's silhouette scores. There's when we're doing we talked about evaluation metrics, and there for PCA there's a silhouette score, but that there's also variance explained. We'll typically, one of the things that you'll see is explainable variance is something that we talk about regularly. And another, there's also what we call, there's singular value variance that we can we can get in our model evaluation. Another one that we'll get is explain variance, the ratio, and that's something that we'll cover that as we get into doing an example here in our lab. But each algorithm has a different model evaluation metric. Some of them have some standard ones, and some of them are a little different. I showed you one where last week it was supervised linear regression, and we used an R-square value, and that's not something that we use in a PCA. In a PCA world, we actually have just an explainable variance ratio. Similar, different math, not but it is an evaluation metric rather that we'd use. So there's definitely a again, as you get into the different use cases and applying machine learning methods to different use cases to solve different challenges, you're gonna have different evaluation metrics, and sometimes you'll create your own. You'll create your own test cases and your own evaluation metrics outside of the standard. So it's something that you learn as you move along, and each algorithm, each technique, each system is always got its unique little challenges. So let's move on to a couple other things. So a lot of times, I think one of the biggest things, the question I get is like, well, of course, what's the difference from supervised versus unsupervised? And of course, the big one is training data, no training data, labeled, not labeled. That's the biggest one. The other one is unsupervised learning models are used not for predictive purposes, but they're used for categorization, descriptive purposes. Tell me what's going on in the data. Describe to me what's going on in the data. That help me understand what's going on today as it relates to the data that I'm looking at. So it's a data under observation perspective when we're talking about unsupervised learning methods. The other piece of that, on the flip side, is that supervised learning methods are predictive. They're forecasting, and they're looking ahead. And so the idea is that it's not so much descriptive, show me what's going on, but okay, yeah, here's what's happening, but then predict what's going to happen next. That's what supervised learning is about. Of course, the use cases are different in the sense that, like supervised learning, I can create predictive classifiers, which is like an image that's not like it is an image recognition task. So in other words, if I create a random forest, which is an ensemble method, I can create a predictive classifier to do image recognition and then to predict what it is that I'm looking at. And there's a probability of, yes, I'm classifying something, but what is the probability that what I'm looking at is a cat or is a dog or is a banana or is a whatever, right? So that's something that is different from an unsupervised world, where it's a just give me the patterns in the data, and then I don't necessarily have a prediction on it. Just show me what the explainable variance and what I can explain in the data descriptively. So it's a very different perspective when we're talking about supervised versus super versus unsuper. So soup versus unsup. There you go. Okay. Let's see. Let's go ahead and talk there. So I want to talk through dimensionality reduction and what this means, because it's a big component of PCA and a lot of other unsupervised machine learning algorithms. So typically, so what dimensionality, when we talk about dimensionality reduction, what we're talking about is taking a high dimensional space, a high dimensional data space, and then reducing that to a lower dimensional data space. And that allows us to take and explain the variance of a given data set and narrow it down to a particular two components, but then also explain the variance between those two components so that I can determine a level of variance before I move into more advanced models. And that's the big thing that I want you to take away from this, is that dimensionality reduction is an amazing tool for not just, it's of course required, but it's also really nice in the sense that me as a machine learning engineer would then be able to say, okay, well, I can do A/B testing on my data set. I can take little pieces of some dimensions within a higher dimension, and then go and say, okay, which side of the data is more variant than the other? That's really what I can do with dimensionality reduction. I can do that quickly. I can split my dimensions in half. I can do, let's say I had 20 dimensions and I needed to reduce that, but then I want to, I'm required to reduce that. But then let's say when you look at a dimensionality and a variance explained and in 20 dimensions, it's going to be hard to get a feel for like which side of the data is going to be more variant. So in other words, I can then say, well, I'm going to do 10 and 10. And then if I can get a higher variance on one side versus the other, that means that one side's going to have more predictive power than the other. So, and then I might down select to 4 or 5 and then find out which, just go through a process of trial and error and to find which different set of combinations of dimensions gives me the most variant output. And that's really critically important when we're talking about machine learning, both for unsupervised and supervised, because I don't want to spend time on a piece of data if it doesn't have a predictive explainable variance, or it doesn't have a predictive variant capability. And what I mean by that is if it's very low in its variance, then I can't do that explainable variance, right? It's not going to be probably useful for me to continue on with using that data set if I want to use it for a predictive purpose. So that's why PCA is nice, because you can quickly down select to a particular area or a particular set of variances that you can use that identifies which data sets are more valuable than others. So here's an example. I've got an n-dimensional data space, which is A, and then that's just represented by these boxes here. And that n-dimensional, it can, has a lot of dimensions in it. And so in this case, I've got a data model and entity relationship diagram here that shows, some 1, 2, 3, 4, 5, 6 entities, and then multiple columns within those entities, right, are objects. And so these data objects then, I can then say, okay, from this high dimensionality, I can reduce them and put them into a lower dimensionality space, and then I can plot and then show, okay, well, there's a clustering effect happening here, there's a clustering effect happening here, but I can mix and match my different components of my my data model to find out and figure out which one is more powerful from a variance perspective. So this is just a visual of that, and this is what PCA does. To cluster, it must go through a dimensionality reduction process. So let's talk about PCA. So we're talking about high-level concepts. Let's dive into PCA. So PCA, it's been around for a long time. I mentioned it before. PCA was developed back in the early 1900s. So easily a 100-year-old algorithm. The math behind it has been around for a long time. And one of the really nice things about PCA is it simplifies. It makes it easy to, it's good for doing data analysis as your first prep step into going into more complicated machine learning algorithms. And one of the really nice things about PCA is that it runs fast. I can run PCA on a regular old computer, and I can run it against millions of records, and it's not gonna really it's gonna blast through them pretty quickly. Not every algorithm can do that. So the math that is behind PCA is very, very efficient. Okay, so let's talk about the math. So first up, the first thing that we're gonna go jump into is just the foundations here. All right, and one of the things that we do is this idea of data centering. So we need to align the data around the origin by centering it, and this involves calculating the mean of each feature and subtracting it from. Let me see if I can get this right. The corresponding feature values in the data set. So what ends up happening is this actually ensures that the data set has a mean of zero for all the features, and this typically will eliminate bias introduced by different scales within the data. And this makes it easier to analyze the relationships and the variances typically without the mean. I'm getting mathematical here, but typically without the mean distorting the results. And so that's pretty that's what's going on here. And then next up is we go into covariance. So we create a covariance matrix actually, and once the data is centered, we calculate the covariance matrix. We get a square matrix that quantifies how the pairs of the features vary together, and so that's where the eigenvalues come into play. But each entry in the covariance matrix represents a covariance between the two features. And so there's a positive value that indicates that as one feature increases, the other tends to increase, while and on the other side of it, a negative value means they move inversely. And this is something that we see in core plots. So what we'll do is we'll create a core plot. And typically what we do is we'll do a cross plot, and then we get a cross product of these core plots, and a positive. What that means is there's proportional growth and then there's inverse growth. A proportional growth in terms of, like, if I have a high dimensional data set, and then I usually do a core plot, and then that'll give me an idea before I go into down selection in my PCA. So in other words, in a core plot, what I'll do is I'll lay everything out, and then if I get positive values, then what that does is that tells me that there's a possibility. Doesn't always guarantee it. PCA is usually pretty good about this, but that if there's a positive covariance in my core plot, then that means that as one grows with a particular variable, it's showing a growth proportional in the other variable. And think of like plant growth and water, application of water. As those both increase, if I increase my water, plant grows. If I decrease my water, plant doesn't grow. So that would be considered a positive. And then there's other things where it's a negative, right? If it's an inverse. So an example of inverse is if I spend more time partying and not going as a student, let's say, and less time doing homework, then that has a negative impact on my GPA, right? That's the inverse. And so as one goes up, one goes down. That's typically how that works. Now, unsupervised, the language and the terminology we use for unsupervised is different in the sense that we don't typically use IVDV language. In other words, you don't use independent variable, dependent variable. We're just looking for the descriptive, is there a variance between these two, in a core plot anyway. We're just looking for a feature. So typically we'll just call it a data feature. And so that's typically what the language is. We're not trying to assign if this happens, then this happens in a hypothesis, which is typically what we do in the supervised world. We don't do that in the unsupervised world. Okay, so yeah, I think that kind of covers this piece of it. So this 2.3 here. So once we get through the covariance matrix, and what we'll do is we'll solve for the eigenvalues and the eigenvectors. And the eigenvectors point in the direction of what we call maximum variance, and that's maximum variance called the principal components. So this is something that the eigenvalues indicate how much variance is captured in each direction, and then so a way you can kind of visualize this is you can think of the eigenvectors as kind of like physics in a way. It's, if you remember, like vectors, right? It's a direction. It has directionality, and that's the same concept here. Eigenvectors rather. You can think of them as arrows pointing to where the data spreads the most, and the eigenvalues as the magnitudes of the spread. And so it'll make more sense once we go into the lab. We're just talking textually. It's always hard to kind of put that all into play when we're talking about this from this perspective. But next up, excuse me, is we're selecting the principal components, and then so what the PCA does is to reduce the dimensionality. There's a ranking process that occurs with the eigenvalues, and typically it's in a descending order, and they pick the top. So the algorithm picks the top K components that explain the majority of the variance, and so that's typically what ends up happening. And so, for example, what'll occur is the first two eigenvalues account for 90% of the total variance. We might choose those two components to represent the data, and then what'll happen is this decision typically the decision balances out the simplicity and the retention of meaningful information. Yeah, say that a few times fast, right? And typically what that does is it ensures that most patterns and structures, let me say that again, most patterns and structures are preserved while reducing the noise and redundancy of the data. So that's something that again, when we're doing this principal component selection, oops, I'm jumping ahead. This is kind of in support of what we do next, which is projecting the data. And so now that the principal components have been selected in the prior step, what will happen is there's a transformation that occurs from the original data and then puts into a new coordinate system. And so what happens is by multiplying the centered data from earlier with the top K eigenvectors in this step, or I should say in the prior step from the selecting principal components, the data can be projected into a new axis. And what happens is when this occurs, the resultant output is a dimensionally reduced data set. And that's pretty much what'll happen, and I mean, you can take 10 data features and reduce them down to 2. Typically it can be 2 or 3. The algorithm we work with, I think, only does 2 components on its reduction, but other reducers can do it into, it gives you the ability to do a reduction in different ways. So for example, I could do a reduction from 20 down to 5 using a different algorithm. It doesn't always have to be down to 2. PCA just works down to 2. There is a way to make it work in 3, but most of the time it's you'll see it in 2. 3 dimensions There is a three-dimensional view of it, and but a lot of times it's usually a two-dimension, a reducer that goes down from multiple to n dimension down to two. So there's a process here. I'm just going to leave this up. I'm not going to explain each one because I essentially just explained it already, but I'm going to put it in here. This is an example of like, I'm just going to say, hey, here's this data X, this X data set. It's a sample set, and you can actually run this by hand if you want. We do a data centering, then we do a covariance. We find out where the variances are in our core. This is a core plot right here. And then what will happen is we'll take the, we get the, we determine the eigenvalues and the eigenvectors, and then we take V1, we take V2, and then we choose K equal 1, and then that's your principal component. Whoops. Okay, then you get a principal component W1, and then we project the data, and then the data is now reduced, in this case, one dimension. And so we this is just a quick way to show that. So, okay, if you want to see it, and there are a lot of YouTube videos online if you want to learn more about PCA specifically. There's books just written on PCA. Whole treaties and dissertations written on PCA. I'm doing a very high level summary of it. But PCA, the applications of it, you can do a lot, right? Data compression, 3D visualization, 2D visualization, noise reduction, pre-processing before we send data over to other algorithms, because we're vectorizing the data. So when you do it's a post-vectorization process. So when we work with PCA data, you take the data, you reduce it, and there's a vectorization process that occurs just through the math itself, and then that vectorization process can be used as a preprocessor to other algorithms. So in other words, that dimensionally reduced low dimensionality from high dimensionality can be fed, that those values can be fed to another algorithm for further processing, for further downstream processing. So it's kind of cool in that respect. Okay, that's all we got for our lecture. If you've got any questions on this, definitely feel free to text or email. But that's all we've got for our lecture. We're gonna head on over to our first lab, which is going to be an unsupervised learning demo for PCA clustering. We're going to be using scikit-learn, and pretty much scikit-learn. I don't know that we'll get TensorFlow or PyTorch. That's kind of more if we're going to get into the t-SNE area, and we're not going to do that for our first lab this week. Okay, that's all I got, and we will see you in the lab.